Dear participants, today is the 11th session of this international workshop on digital image processing. I am very happy to share with you that today Sandip Kolekar sir, Chhatrapati Shivaji College Satara, he is with us and he is going to talk about image enhancement and transformations and his focus will be on spatial enhancement. I'm sure you will enjoy his deliberations. It is our prime duty to introduce today's speaker. So I request my colleague kindly introduce today's speaker.
Thank you,
Nitin,
sir.
yeah, please continue.
Yeah, sure. Uh, I'm audible to everyone.
Yes, please
Madam.
proceed ahead.
I'm audible. I'm audible.
Yes,
Yeah,
please.
Yes, yes.
Yes, madam.
yeah. Respected Vice Principal and Head of the Department of Geography, ASP College, Devruk, Dr. Sardar Patil, sir. Respected Resource Person, Mr. Sandip Rishwasrao Kolekar, sir, and all the participants. Very good evening to all. We are on the 11th session of this 16 days training program on digital image processing. Sir, before starting the session, I would like to give his introduction. So, sir, if we consider sir's academics, sir has completed his BA in geography, BA in geography from Mudhoji College, Satara. Sir's a master in geography from Pune University. PG BSc Department of Geography from Pune University. Currently, sir pursuing PhD from Pune University. Sir has completed 3 e-learning courses from IIRS Dehradun, even 3 international journal research paper published by Sir, and 7 research paper presented in various conferences. PG Diploma Research Report supervised, 9 total PG Diploma Research papers supervised by Sir, and 17 guest lecture delivered by Sir, and even Sir have awarded as a Best Reader Award in 2019-20 Shivaji College, Satara, and his industrial experience of 2 years in TomTom India Private Limited, Pune as a digital cartographer. Teaching experience 10 years as an assistant professor in geography in Rayat Shikshan Samsa Satara, and various subjects taught like GIS, RS, photogrammetry, even coordinator of NIRF of Chhatrapati Shivaji College, Satara, member of various committee like UGC Proposal Committee, COC and PG Diploma courses, Avishkar Research Committee, and if he considers other experience in various audit like fire audit, green audit, computer audit in various institutions, and even successfully faced local inquiry committees coming for affiliations sent by university. So we are welcoming you from behalf of Devruk Shikshan Prasarak Mandal and all the collaborating institutes. So, hello. So
Yes, ma'am.
you can start your session, sir.
Yes, ma'am.
Thank
Thank
you
you.
so much, sir.
Thank you.
Yeah.
Thank you, Kambe ma'am, for such a very elaborative introduction. Also, I would like to thank you, Vice Principal and Head of Department. Am I audible, sir?
Yes, sir. Kolekar sir, please proceed ahead. You are
Yes,
very
sir.
much audible.
Yes, sir. And thank you to Vice Principal and Head of Department of Geography, Nyamurti Tatya Sahib Athalle, Arts, Vedmurti S.R. Sapre, Commerce, and Dada Sahib Pitre, Science College, Devruk. Actually, it is an autonomous college, District Ratnagiri of Maharashtra. Uh, I'm welcoming you all participants on behalf of uh, not only the Nyamurthy Tatasai Patilli College, but also we are one of the uh, collaboratively organizing institute. So on behalf of all the institute uh, and the Atalli College as well, we are welcoming you in this particular international workshop on digital image processing. And thank you once again, sir, to given an opportunity here to talk in this particular international workshop. So uh, let me just share my screen first. Okay, okay, okay. So today I'm talking on this topic, that image enhancement and transformation. Basically, this is an main topic and subtopic which is allotted to me, that is a spatial enhancement basically. Uh, in that the convolutions, high pass, low pass and band pass filter. Then we are discussing about the edge detection and edge enhancement as well. So it is little bit very tough target to in front of me, because it is very elaborative topic to discuss in a single lecture. But sir, actually we discussed 2 week before that. We sir, you has trying to request me that please try to give an 1 or 2 days in that particular topic as such. But it is very uh, due to this very uh, uh, the schedule is very tight as far as our Chhatrapati Shivaji College is here. We have also an hands-on training program in our college. That's why it is very tough for us. Okay, but though it is, we can trying to cover all these things today's lecture. So thank you once again. Let's proceed with this subtopic, that is spatial enhancement, convolutions, high pass, low pass and band pass filter with edge detection and edge enhancement. So before we start, we should know the digital image. I think the most of the, this is an 11th day. Am I right, sir? Yeah. So this is an 11th day. Still today we definitely the participant understood that what exactly the digital image is. But I just recap this part, that what exactly the digital image is. So digital image is represented by the rectangle array of integer. So we know that digital image is the image which has a pixel value, and it is nothing but it has an array with confined with the rows and column as well. So here is the actually mathematical representation of this digital image. So we know that the value of this image is a pixel value. So here is the n is the uh, actually rows, m shows the columns and q shows the gray levels, means the dn value, that is the what exactly the reflectance captured by the sensor, it is represented by the q. So it is uh, given as a gray level. So if we have the uh, uh, 8 8 band or 8 beat pixel, then 256 is the value or maximum value of gray level. So we know that. So that's why here the value of q is a dn value, and it is an integer number. So we know that the integer number is a nothing but it's a discrete number. It is not in a fraction, it is an integer number. So here is the mathematical representation, that f is the function of that particular pixel, and the location in the form of, let's see here, 0 comma 0 is the first pixel, then 0 comma 1 is the second pixel, and like that it is so on. So this is a little bit about the digital image. Actually you may know that, but I need to recap again, recap your knowledge as well. So this is a pictorial format of this image coordinate system. So here is the coordinate, that x and y here. So what exactly x and y? X and y is the pixel location here. So here is the actual value and the pixel will get the value of that. Means whatever the reflectance from this particular area, it is represented by here. So this pixel is represented for all the reflectance from this all area, that is the this value. And this value, we know that we already talked that told that I have told that this value is in the grayscale, means in the form of digital number. So I make it very simple. Let me show this is a real world example. That is, this is an house. This is an linear feature, that is a road, and another is the archaeological sites. So when we are going to represent it in the form of raster data, so it is here that, let's say here is the, you know that the house. So house, it is in the very little part of this particular pixel, but we know that it is an spatial resolution. We already the in that particular workshop, we may you may know that this is an average value of this pixel, means house is here, but other it may have the grass and all other things around the house, but all these reflectance get average and will get the value of this particular. So major reflectance is dominant on that particular pixel value. So here we can show the house in the form of this pixel. Now this is a linear feature, it is shown by the sequential format of the pixel, and we'll get the value of we'll recognize that this is a linear feature. And on the what can say that association, all these things, the interpretation elements, we can easily detect that, easily interpret that this is on the basis of color, tone, and association feature will recognize the feature that is in road actually, or the river. Now this one is the archaeological site. Again, it is depicted by the pixel and likewise. So this is a general view, that is a very basic fundamental of GIS or the remote sensing. That is, the raster data is represented with the number of rows and number of columns. It is an array by combining of the rows and columns as well. So here we'll get the value of the pixel, that is house. It is not like that it is an h is there, but actually we'll get this value in the form of numbers. So this is an full picture that I would like to tell. So let me tell you about some file format which is available over here. Uh, that is, one file format is missing here. You may remember that IMG, it is another form of image file format. That GIF, graphic interchange format. This is PNG. We know that Microsoft recently basically recommended that particular PNG file format, and which is well-known image file format, that is portable network graphics file format, named JPEG actually, Joint Photographic Expert Group, TIFF, which is very famous in the now. GIS vendors are recommended that uh, the file may be transferable. Basically, raster file should be in the TIFF file format. So tagged image file format, this is file format, or some in software it may called as a geotiff. So there is no any difference between TIFF and geotiff name. PGF is there, portable gray map. Then FITS, flexible image transport image, and one is missing, that is IMG file format, imagine file format, which is basically compatible with the ERDAS imaging file format. So now let's see how exactly the picture is captured or the image is captured here. Illumination energy, and here is, let's consider that this is an sun. So we know that the sun is our ultimate source of energy. So sun propagate this energy towards the earth's surface, then illuminate this particular object. The scene is illuminated, the light is reflected from this particular object. Then imaging devices capture this particular whatever reflectance, irradiance, we can say that. So it is captured by this sensor. Then what exactly in the sensor internal imaging plane, this is like that in the form of, let's say, grid, and output digitized image or digital image is that. So why we called it as a digital image? Because there is no any color in that. So all these things in the form of numbers. So this is nothing but this is a number. So higher is the number value, higher the integer number value, then the grayscale is the darker, and lesser sorry, higher is the number, the brightness is the higher, and vice versa. That is, lower is the number, the grayscale turn towards the dark one. So this is like that. So an example of this digital image acquisition process. Let's see the energy illumination source is in here. That, let's say A. Then an element of the scene, that second. Then imaging system is here. Then projection of this scene onto the image plane. Okay, and final product we got this. This is an output digitized image. So this is an actually the process of acquisition. So let's discuss about the what exactly the digital image processing is. So digital image, we know that a two-dimensional function, that is function of x and y, and the another value we know that this is a digital value, means the pixel value, digital number actually. Then x, y are the spatial coordinate. The amplitude of f is called as a intensity or gray level at the point of xy. I already told that this is a function, means the value of pixel, means it is a value of reflectance. In another word, we can say that it is a value of reflectance which is reflected by the object from the earth surface or any celestial body, we can say that. Digital image processing. So what exactly this is? So process digital image by the means of computer. It covers low, mid and high level process. So there are three types of image processing. First is the input and output are images. So low level images includes only input and will get the final little bit refined version of this particular input. Then mid-level processing is includes output are attributed, extracted from the input images. We'll explain you in the next slide what exactly the thing is that. But it is little bit, we'll get the attribute from this extracted image. So when we input the output this data from the first level, we'll get the output image. Little bit from this we will get the attributes, some information from that. Now, the last one is the type that digital image processing is high level image, and this is an assemble of recognition of individual object. So here we can recognize the object. So this is a final stage of image processing. Then we'll get the proper thing, proper the knowledge of proper object identification in that particular level. Now the pixel, the element of digital image. So pixel, tessella, cell is, are the synonymous word. That is, the pixel is the very basic element of, basic ingredient of digital image. So here is the sampling and quantification of the image. Let's see, this is a cross section of this image. So here is the A and B. So A and B, we know that this is an actual body of part, and here is the we'll get the actual cross section over here. Then generating the digital image, that is the continuation of the image. Then a scan line from A to B. This is a scan line from A to B. Okay. Then we'll get next one is a scan line from the A to B in the continuation of image, used to illustrate the concept of sampling and quantization. Then sampling, quantization, image digital line. So same thing, I already told you that this is the process, and here is the elaboration is here. Means this is an sampling. Out of this scanning, it is now let me show you like that. here is the value, then we'll get the this average value of this reflectors. Means here is the, let me show you again. Yeah, so digitizing the coordinate value, here we can here is the analog signal, then we convert it into the digital number. So here we'll get the few the digital number, the digitized amplitude values will get in the final product. So this is a digital scan line over here. So here is the actually cross section and how it get the quantified and how will get the pixel value actually. So after the scanning this image and converted into the digital format, it will get the in the form of pixel. So here is we can say that it is a very coarse resolution. That's why it not get the proper shape of the original. So this is an continuation of image projection and the sensor array. But here is the result of image sampling and the quantification. So here is we can say. Now we know that what exactly the element of remote sensing and like that. So I'm not going into the detail that we need the energy to get the knowledge of this particular object. So here are the three things we need. That is, one is object which we want to sense. Then we have the sensor. Of course, here is the natural sensor. We have our eyes are the natural sensors, and from get this information remotely, we need the energy carrying waves. So there are two actually theorem is that energy transformation theorem. One is the wave model, another one is uh, quantum model. That is it is in form of packets. So basically, we are most of the physics physicists are very much do their research on the wave theory. That's why we accept this particular wave theory. Means electromagnetic waves are there, which transfer this energy from object to the us or the from to the sensor itself. So this is all about the what exactly the remote sensing is done, and this is we know that this is a spectrum. This is a part of visible band. Beyond in remote sensing, we have an ability to sense beyond the visible band. So this is a ability of remote sensing uh, guys can give the information beyond the visible band. So other people get the knowledge in within the visible band, but the remote sensing or visual informatics scientist or the geographer will have and to see the beyond visible. So this is actually, we know that this diagram most of the time you may see that that is the this is a source of energy. Then this is a reflectance, means it is called a reflective remote sensing. So there are three types of remote sensing: that reflective remote sensing, thermal remote sensing, which is actually emitted by the earth surface of the object from itself. So there is no any source. Actually there is a source because our, let's say the terrestrial our part earth is the part, but it get heated from the sun itself. So emitted energy which is captured by the sensor, it is in the thermal remote sensing. Then microwave remote sensing, it has its own source of energy. It may have a emitted energy, but most of the time micro remote sensing, it is an active type of remote sensing because it has its own energy type. Okay, so here is the wavelength band is here, 0.3 micrometer to 3 micrometer. We know that, so we just, this is a actual spectral signature pattern. What I'm trying to tell you in the form, why I'm showing this, because I'm just recapping the things that what exactly the things are there. Then it will be easy to go ahead. Now this is an I'm not spending much time on that. So this is an dry grass, soil, green grass is here. So we know that when we found the little bit the less water content, it get reflected more. So in visible band, let's say here is the visible band, and let we know that the crop is the vegetative cover, or the it has an chlorophyll, so it reflected more in the NIR, means infrared band. So it is more than 4 times reflectance is more in the near infrared band. So uh, that's why here is the graph is picking toward the 40 percentage reflectance near about 42, 45, and here is the in the green near about 8 to 7 percent reflectancy. So this is all about the general spectral signature that we already know in the basic remote sensing. So let's discuss the main part, that is a free GIS remote sensing data source. We know that we should know that these are the, and you may know that these are the some sources from this. We'll get the free remote sensing data from the various sources. So before we start our topic, we know that the digital image processing, DIP, is the extremely broad subject and involves the procedure which mathematically complex. So these are the three types. I'm not spending much time on the things, but image rectification is there. Let me uh, tell you that where our image enhancement is existing. That's why I'm showing you what exactly the process is that. So digital image processing is the extremely broad subject and involves the procedure which mathematically very complex, because everything is done on the basis of mathematical, it is computed algorithm behind the scene. Okay, so we'll get the output in the form of color image and sorted image, that the classified image and all these things, but actually the very complex mathematics is actually algorithms are running behind the scene actually. So that is the part, that's why the digital image processing is defined as a mathematically complex procedure. So that's why it is called as digital image processing. Got it? So here is our location of image enhancement. So today this is the broad topic that we have to discuss. So let me tell you that first is the among the digital image processing. This is an image rectification. What is rectification? So this is not our topic, but I need to little bit go through this. This operation aims to correct the distorted and degraded image data to create a faithful representation of the original scene. This involves what it involves: to calibrate the data radiometrically, to correct for geometric distortion, to eliminate noises present in the data. So these are the main three basic aim of this particular rectification. So I think you people may know that in earlier lecture, it may clear to you actually. That's why I'm not discussing much on that. So next is our radiometric correction. So this involves the rearrangement of DN value in the image, so that all areas in the image have the same linear relationship between DN and radians. So here is the radiometric correction. It is a little bit about the rearrangement of the DN value. So what are the causes of radiometric errors? So detector imbalance and atmospheric deficiency. Actually, it is already discussed in earlier lecture. So this is because of the radiometric errors are there, and we need to rectify before we go further. Then last is the image classification. Image classification intent to classification process is the categorize all pixel in the digital image into the one of the existing land cover classes. The traditional method of the classification mainly follows the approaches. We know that the two approaches are very famous, that is supervised and unsupervised classification. So these are the two basic classification methods are very famous for that. Sorry. Okay. So sorry. Yeah. Let's see. Let's come and come to discuss that the image enhancement. So before we start the spatial enhancement, we should know the what exactly the image enhancement is. So image enhancement is nothing but it is a modification of an image to alter its impact on viewer. Okay. Enhancement are used to make it easier to visual interpretation and understand of imagery. So what exactly the image enhancement is? So enhancement is modified the original image. Why we modified it? Because this image or this enhancement make it easy. What it make easy? It make easier to visual interpretation and understanding. So this is our main goal of geoscientists, that we can get the final information from this remotely sensed data. So that's why we need the image enhancement, because most of the time what happened, so many errors are there, because satellites are flying hundreds of kilometers above the earth's surface. So it is not an easy task to get the proper picture or the proper reflection from the earth's surface. So many things are there. Atmosphere is there, uh, let's say clouds are there, so many noises are there, satellite has an errors are there, so ccds are not working properly. So these are the so many stumbles are there. So that's why uh, it not get the proper data. So that's why we need the image enhancement. So through enhancement, it is very easy to visualize, to interpret, to understand what exactly is the image. So next is the process of making an image more interpretable for the particular application to accentuate the certain image feature for subsequent analysis or image display. So here we actually subsequently will get the image display, or the same thing is that for the process to make very easy, to get easier to understand any feature, that let's say we want to uh, study the linear feature, that's a river. So we should have to do a particular edge enhancement. So it will get the proper edge detection, will get the proper discrimination from the river and the other the bank, other part or other land use, we can say. So for that we need that particular enhancement. The another importance is useful to, since many satellite images give inadequate information for image interpretation. Okay, so we know that I already discussed here that the satellite image gives inadequate information. So there are so many reasons that the information is not adequate. So it may inadequate. So to get enhanced, to get the information, proper information, our proper results, we have to do the image enhancement. Now attempted after the image is corrected from the distortion. So it will be helping that part as well. Now may be performed temporarily or the permanently. So it may be used as a temporarily or permanently as well. So here's the, in a raw imagery, the useful data often populated only small portion of the available range of the digital values. Commonly, when we are talking about the 8-bit data, so 2 raised to 8 means we'll get the value of 256. So gray scale means the DN value is up to uh, uh, a maximum value is 256. From 0 to 255 values will get the DN value, because we when we are talking about the 8-bit data. Right? So this is about the image enhancement process. So there are three types of enhancement type. Okay. First is the radiometric enhancement. Second is the spectral enhancement, and last one is the spatial enhancement. Okay, so here we are talking about the radiometric enhancement first of all. So what is the radiometric enhancement is? So radiometric enhancement is a modification of brightness value of each pixel in an image data set independently. Basically, it is known as a point operation. So radiometric enhancement is basically a modification of brightness value of each pixel. So here we are only dealing with the DN value. This means the brightness value. So radiometric enhancement is basically point operation, which is basically deal with the value which is related to the brightness value, means pixel value. Now the spectral enhancement. What is the spectral enhancement? So spectral enhancement means the enhancing the images by transforming the values of each pixel on a multi-band basis. So when we are talking about the spectral enhancement, so multiple spectral bands are involved in that case. So enhancing image by the transforming the value of each pixel on a multi-band analysis. So here we are considering the multiple bands here. But today, our today's subtopic is a spatial enhancement that I would like to more emphasis in the today's lecture. That is a spatial enhancement. What it did, it basically uh, confined, that is a modification of pixel values based on the various value of pixel, that is a DN value. So let's talk about the spatial enhancement. So before we talk about the spatial enhancement, we should know the spatial frequency. So here is the image. Please try to see it carefully and try to find out what exactly the difference in between. Okay. Yeah. Yes. Just a minute. So here we found we can see that the two images are here. So first one is a radial variation in the grayscale and slowly varying the changes in the grayscale. So first is a high frequency image. So these two images are the images. The first one is the high frequency image and second one is low frequency image. So what is the basic difference between the high frequency image and low frequency image? Let's understand. So let's say the high frequency image. So the texture of high frequency image is rough. So it has a rough textured area of an image where the changes in tone are abrupt over the small area, have a high spatial frequency. So we found that the very high or the abrupt change in the pixel value. So there is no any smoothness over the image. So that's why it is called as a high frequency image. So how to recognize the high frequency image? When we found the abrupt change in the pixel value, then the same image is called as high frequency image or the part of the image. So it is not only image, but also when we somewhere we are some people ask that what exactly, try to find out the high frequency area in the image and try to find out the low frequency area. So homogeneous area we will see in the more example in the next few slides. So we'll get in that case the high frequency and low frequency in the same image. So this is about the high frequency image. So what are the characteristics of high frequency image is the pixel value changes abruptly over this small area. This is a very basic characteristics of the high frequency image. So next is the low frequency image. So what is the characteristics of low frequency image? So a, it's look like a very smooth area. And why it is look like the smooth area? The Because it has a little variation in the tone over several pixels. So it is not changes abruptly like high frequency image. It has a very smooth texture because it not changes abruptly over the small area. So several pixels we found the same value. That's why we found very smooth texture over the tone over the pixel, and we called it as a low frequency image. So this is a basic difference between low frequency image and high frequency image. Low frequency image looking a very smooth area, though other hand the high frequency image looking very rough texture. So what is the spatial frequency? So spatial frequency, the number of changes in the brightness value per unit distance for any particular part of image. So it is number of changes in the brightness value. So how it is when we called it as a high frequency? So brightness value changes very abruptly per unit area. Means a small area, we found that the value it changes very abruptly. So composition, I already shown you that this is an high frequency details and low frequency details. Means the per unit area the brightness value changes abruptly here, and very same value we found for the several pixel or the per unit distance. Now low frequency details few changes in the brightness value over the given area, but other hand the higher frequency details brightness value changes dramatically over the short distance. Let's see the example in the next. uh, this is an pictorial format of the spatial frequency. So here is the example. First is the zero spatial frequency. So we can say that there is no any changes in the pixel value. So it is a flat image in which the every pixel has the same value. Okay, so in the zero spatial frequency we do not get any value over the images. It is very flat. It is let's say it is a zero value actually. So there is no any changes. Actually it is not a zero, let's say, yeah, but there is no any change in the spatial frequency. So flat image in which every pixel has the same value, that's it is called as zero spatial frequency. Now let's talk about the low spatial frequency, an image consisting of a smoothly varying grayscale. So let's say here the grayscale is gradually changing over the area. Let's say this is a darker one, little bit darker one, then slowly it get the brighter one. Now it is not changing abruptly, it is very smoothly varying the grayscale over the area. So that's why it is called as low frequency, low spatial frequency. Now let's see the last one is a high spatial frequency. So an image consisting of a checkbox or uh, checkerboard or black and white. Let's say it is an like that. It is abruptly changes the black and white value. So that's why we already discussed. We are already spent much time on that, which is then abruptly changes the black and white value, means the pixel values are abruptly changed. Okay, so let's talk about the spatial filtering. So what is spatial filtering? Okay, so spatial filtering is nothing but I missed one example actually. Here is my example. I don't know. Yeah, here is the example. Low and higher frequency. Yeah, let's say this is in sequence is going to change. Let me show this. So this is an actual example of low and high frequency identity. So identification of high and low frequency. Let's see the real world example. This is an image, and this part is enhanced over here. Okay. It's magnified over here. Let's see. So here, when we found the homogeneous part, let's say it is here is the vegetation cover. So we found the very smooth texture is here. But when we going to add the edge, here is the edge, means it may a barren area. So it is an edge, and here is the edge, and will get very abrupt change in the pixel. Okay, so at the edge we found very abruptly change in the pixel value. So here we can say that here the high frequency is there, but here spatially high frequency is there. So spatial high frequency, and here we can say that very low spatial frequency is there. So understand, that is the main basic difference between the high frequency and low frequency. The example is that. So this is a real world example, that is a high frequency details and low frequency image. So let's talk about the spatial filtering. Okay. Yeah. Just a minute. Yes. So what is the spatial filters? So spatial filters are dividing the image into the constituent spatial frequencies. Just a minute. So before we talking about the actual spatial enhancement, we should know the concept of few which are very needful for to understand the enhancement. So spatial filtering, which divide the image into the into its constituent spatial frequency, and selectively altering the certain spatial frequency to emphasize some image features. So we use some filters. We know that the filters, but here we are using the filter that some feature are enhanced with the help of that. So here is the dividing the what exactly the filters are there. Now let's talk about the next filter. Just a minute. I'm not getting actually proper. Yes. Just give me 1 minute. Okay. So spatial filtering. What is the spatial filtering? So spatial filtering is the process. Okay, is the process of dividing the image into its a constituent spatial frequency and selectively altering. So when we want to emphasize some feature, we need we are a geographer or a geoscientist needs to study some feature. So in that way, we can do the various analysis with the by using the various type of filters. So we will see in the next few slides that what are those filters are using with the help of the target target oriented filters are there. So we will discuss in the next few slides. So here is the spatial filters are the filter which we use the filters to emphasize some image features. Now what is the second part? To process suppressing. So what it's suppressing means, the process suppressing is the de-emphasizing. What is mean by process suppressing? So de-emphasizing certain frequency and the passing emphasizing the other. So when we want to emphasize something, let's say I need to draw a river boundary. Okay, so I need to emphasize a edge of this particular river. So, but I need not to enhance the area which is very recent to this, very next to this. So in that case, the process suppressing we are using in that case. So filter, spatial filter help in that case. So edge detection as an edge enhancement are the two do part in that spatial enhancement. We will see in the next few slides. But here we can enhance something, we de-emphasize something, and we emphasizing something. So what part we want to emphasize, we can emphasize it, and which part is we want to de-emphasizing, we can de-emphasize in that particular part. So understood what exactly the process of suppressing. Now next part is the increasing the analyst ability to discriminate the details. So the techniques, the spatial filtering techniques increases, what it increases, the analyst ability to discriminate the details. So to understand what exactly difference in between, so we are very much we are it is very helpful, the spatial filtering in that case. The next is the local operations. So what is local operations? So local operation, that is the pixel value is modified based on the values surrounding it. So local operation, local operation, we know that the zonal, local, so these are the some raster operators or the operations. So local operation, if the spatial filtering are the local operation, which basically which is nothing but it is a pixel value is modified based on the value of surrounding. So surrounding, on the basis of surrounding value, we are going to apply this filter and will get the enhanced image, spatially enhanced image, more specifically. Okay, now next is the used of enhancing certain features. So uh, to what exactly the spatial filtering is did, it helpful to used for enhancing certain features. So certain feature we want to, like let's say I just give you an example, age we want to enhance. We want to enhance some land use. So in that case, we can use the spatial filtering. So in that case, we use the spatial filtering. So removal noise. So noise removal is very useful characteristics of the spatial filtering. We can remove the noise with the help of spatial filtering. And another one is smoothing of image. It is very common use of spatial filtering when we want to smooth the image, because we know that the high frequency image are very rough image. So if we want to make it smooth, then we can use the spatial filtering. So this is one example. So many examples we can take in that case, that when we want to smooth the image, then we use the spatial filtering. So in that we can get the smooth image. Okay, so I already discussed this part. Okay, just a minute. Yeah. Now let's talk about the filters. So what type of filters are there, or the what exactly the filter is? So yeah, here we are. So filters are the algorithm for filtering. So filters are the algorithm for filtering things that composed of window mask, corner, convolution, mask, and the contrast weight given to the mask. So filters are not a uh, very tough task. It is a kernel. It is a convolution mask, like that. Here is the example. So what is the basic part of this mask? So it should have a central value. So it is only thing that we can't say that 2 by 2 is the mask. So we can't say that this is a mask. So mask would be a 3 by 3, 5 by 5, 7 by 7. So we'll get the central value. So this 3 by 3 mask, when we get the center value or like that. So it is it would say in the matrices it is a square matrix, means number of rows is equal to number of columns, like that. So here is the filters. So filters are the algorithm. We know that the digital, that's why we learn first of, we just recap that what exactly the digital image is. Digital image is the nothing but it is a array of pixel, and pixel has a DI value. Got it? So here we can see that this is an kernel we use. Let me just put this one. So here we is a 3 by 3 filter which has a 3 columns and 3 rows. So that's why it is called as 3 by 3 square mask. So again, I am repeat that the filters are composed with the Windows mask, or the kernel, convolution mask, or the contrast weight mask. So here is an example of 3 by 3 mask. So what is convolution? This is our subtopic point. What is convolution? So convolution is the filtering techniques. A linear spatial filter is a filter for which the brightness value, that is a BV means brightness value. Let me tell you that BV means what? BV means a brightness value. Let me just, yeah, BV means brightness value. Brightness value of Ij out at a location of Ij in the output image is the function of some weighted average. Let me tell you that. Let me unlike this word. It is a nothing but it is a weighted average of linear combination of brightness value located in a particular spatial pattern around the Ij location in the input image. I will show you in the graphic, so you will understand better than this very. Because that the words, it is very tough to understand, but let me just tell you something that it is a some weighted average is that it is weighted average of what? It is a particular pattern, and this is a very important word, that is around locations. So filters are get averaged. It is not average only, it is a weighted average of that surrounding pixel in the input image. So process of evaluating the weighted neighboring pixel values located a particular spatial pattern around the location input value. Let emphasize this word, that around the Ij location. So let underline this word, that's around the Ij location. This is a very important word. Okay, so let's go ahead. So convolution is the example of convolution filter is the coefficient of C1 is the mass are multiplied by the following individual brightness, that is the value of BVI in the input image. So this is a mask template. So BV5, let's say I will not going to uh, uh, spending much time on that. Let's say we, because we want to uh, finish our lecture within a time. Let me just erase this one. Yeah. Okay. So here we want to let me show you. This is an C5. When we want to calculate the BV means what? The brightness value of this cell. So what is the value of this BV? So BV is the BVIJ, means it is the value, brightness value of BV is the weighted average of surrounding pixel value. Got it? It is a weighted average of surrounding pixel value. It is very simple math. So let me just go ahead. So here is an example. This is an 164 is the digital value. We know that It is a DN number value. It is a brightness value, BV. So BV5, let's say here is the BV5, 3 by 3 kernel we used over here. So here is the window mask. And what exactly we use? That is a 0 1 0 1 1 1 0 1 1. So this mask we are going to use here. So when we put on this particular image, this is an actual image. These are the some values. Only these are the colors. This is an grayscale, but behind that we know that a digital image has a brightness value, digital number value. So 164, 188, 164, 178. So these are the actual DNA value. Now this brightness value is multiplied by of each mask. That is the 164 is multiplied by 0. 1 is multiplied by 188, 0 is multiplied by 164, and so on. And we'll get the proper value. Here is the 932 is the weighted average of this. Now, uh, 6 pixels are there and we want to calculate the middle one. So here we can get the value of this pixel. So how to get? So 932 divided by 5. 5 means we want to weighted average means we multiply this and then we sum this all things and divided by the number of observation is the 5. So we'll get the 136. So central pixel value will get which is very uncommon value, that's 178 17. So it is changes and it is substituted now a 186. So this value is substituted by this 186. So this is actually convolution filter techniques is before filtering we use actually. So before filtering, we see this particular pixel pattern, and after that, we after convolution, we'll get this result after filtering. Got it? So we'll get the more enhanced image than the first one. We'll get the more enhanced the features in the next one. So this is a convolution filter. So let's talk about the low pass filters and high pass filter. So what is low pass filter? Just a minute. High frequency details. Please, please listen carefully. What is low pass filter? Let me just make up. So low pass filter basically, yeah, low pass filter blocks the high frequency details. So we understand why we are studying this particular thing, that high frequency and low frequency, because we are using this particular thing. So blocks the high frequency details. Low pass filters block the high frequency details. And has what it did now. So high frequency after blocking definitely will get the smooth effect of the image. So someone asks you that for the smoothening the image, which filter you are going to use. So definitely the answer is a low pass filter, because why? Because this is the reason. In first line we'll get the reason that it blocks the high frequency details. The image gets smoothened. Got it? Then use for the removal of the noise. So next one is the removal of the noise. So why it is not blocking only the high frequency, it is blocking high frequency, but it is used not only a smoothing image but also the removing the noise as well. Now removal of salt and pepper noise. So we are here is the not we can say that actually 5:12 in the clock. So we need to just go fast. So if we uh, it is removal of the salt and pepper noises as well. So it is very famous noise in the remote sensing. This is blurring the image, especially at the edge. So this is very important, that I'm just squaring this, because it is not enhancing the edge, it is blurring the edge. So our last topic is that the edge detection as edge enhancement. So low pass filter is not a good to enhance the edge. So that's why it suppress the edge. It blur the edges at the linear feature. We are not going to use the low pass filter because it edges are blurred. Now, what is the high pass filter? It preserves the high frequency. So let's say it preserves the high frequency, remove the slowly varying components. So these are the things are here. Now, what is emphasizes? Emphasizes fine details. So fine details are emphasized, used to edge detection. So I just told you now, that is the high pass filter. When you want to emphasize the age, you want to age, detect the age and enhance the ages, so in that case you need to use the high pass filter. Got it? Now ages. So age is the main purpose of this particular high pass filter. So location where the transition from one category to the other occurs, in that case we need to use the high pass filter, because we need to discriminate to part, discriminate to the land use or land cover. So in that case we need to discuss, we need to apply the high pass filter, because it enhances the age, it detects the age, and that's why the high pass filter is used basically. Okay. Now high pass filter. So there are two type of high pass filter, that is linear and non-linear filter. So output brightness value is a function of linear combination of brightness value located in the particular spatial pattern around I and j location. So I'm going a little bit faster, because actually 12:14 in the clock. Now linear output brightness value is a function of linear combination. So in a linear high pass filter, the linear combination of brightness values here. So in the mask, okay, in the mask we are using uh, in the mask we are using the linear function, we are using the linear thing, we are using the linear filter. So I will show you in next few slides that what exactly the linear feature is. So we are using the linear feature. So let me just, okay. So non-linear. So use a non-linear combination of pixels. So when we selecting this non-linear feature, so the mask or the kernel we are using a non-linear combination. Here we are using the linear combination. We will see in the multiple high pass filters in the next few slides. So edge detection, I already told you that. Let me show you in the before slide. High pass filter is basically used to edge enhancement and edge detection. So here, let's say, so edge detection is the main task of this particular high pass filter. So background is lost. So in let me tell you that, please let's understand what exactly the difference between edge detection. Most of the people are making confusion in between edge detection and edge enhancement. So edge detection, what it does, background is lost in edge detection, but edge enhancement delineate the edge and make the shape of detail more prominent, background not lost. Please try to understand these things. So edge detection, in that edge is enhanced, but background is lost. So this is a drawback of this edge detection. But in the edge enhancement, it delineates the edges and make the shape and detail more prominent. So edge details are more prominent. Not only it is make this edge prominent, or that it delineate the edge, but it also cannot lost the background as well. So this is another let's say the things that done by the edge enhancement. So this is the basic difference between age detection and age enhancement. So we should understand that when we're going to understand the high pass filter itself. Now this is a Laplace non-directional filter. So let's say the directional and non-directional, we already discussed that what is the linear and like that. The Laplace is the non-directional. So here the Laplace operators highlights the point, line and edges in the image and suppress the uniform and smoothly varying regions. So it suppress, let's say, Laplace operators, what it did, highlight the point and line edges in the image and suppress, what it suppress, the uniform and smoothly varying region. So it is not emphasizing on the uniform and smoothly region. It is only emphasize the point, line and edge. Please understand. Please try to uh, underline this part. There is a point and edges are basically emphasized by the Laplace filter. To read the Laplace edge detector filter, so in that 3 by 3 uh, mask is here, -1, -1, -1, 8 is the middle one. So Laplace edge enhancement, so middle value is doubled over here and it is again increased by the 1. So Laplace is edge detectors and Laplace, so middle value is getting increased in the edge enhancement and in edge detector it is more than 1. Got it? So because of this, the background is lost in, edge is delineated. That's why the Laplace is the high. It is very important to edge enhancement and edge detectors. So edge detectors and edge enhancement, these are the two filters basically by the Laplace. Okay, non-directional filter. It is called as non because there is no any direction. So all over the values are there. Now, additional edge detectors mask. So here is the horizontal, diagonal and vertical. Let's say horizontal. So middle value are the same. Horizontal value are the same one. There's 2, 2, 2, 2. So that's why it is called as, what is called as horizontal. What is meant by diagonal? So diagonal values are unique. Diagonal values are same. So that's why. Now vertical. So vertical value means column, this column is same. Okay. So the vertical value is a unique value, means same value. So directional edge detection filters are designed to highlight the linear feature. Again, it is emphasized on the linear features such as the road, field and boundary. So when we want to study the linear feature, so edge detector mask we are going to use, and in that case we can use as we need that diagonal, uh, horizontal and vertical as well. Now these filters can also design to enhance the feature which are oriented in a specific direction. So when we want to apply it in a specific direction, when we want to directional, then diagonal, horizontal, in that case we use this additional edge detector mask. Now these filters are useful, basically useful in the application such as geology, for the detection of a linear geological structure. So when we have the linear uh, uh, feature in the geology, then in that case we are using that particular filter. So directional filters, again we have the more directional filter that is on the basis of directions, that is north, northeast. So I'm not going to be not emphasize the thing that this is the north, then northeast, let's say, okay, then east, south, then southeast, then southwest, southwest, let's say, then west and northwest. So these are the filter basically known as a directional filter. Why? The mask name suggests the slope direction maximum response. Example, let's say the east gradient, let's say this is an east gradient, we have an east gradient. Mask produces the maximum output for the horizontal brightness value changes from west to east. So in that case, when we have the slope gradient over there, not only slope gradient, another value. you can take the any geographical value which has an gradient towards the east. You can use this value particularly. So that's why we are studying the directional filters. Now let's talk about the non-linear and edge enhancement using the Sobel operator. So this is an Sobel operator. I'm going little bit fast. Now non-linear edge enhancement using the Sobel operator. So this is the formula for that. So Sobel operator to get the middle value. Okay, Sobel phi out means x square plus y square. So it gave the brightness value of 3 plus 2 to dB6 means these are the pixel number values. So it gave the formulated likewise and will get the x on the basis of this root of uh, x square plus y square. So this is an Sobel operator. So after using this, what exactly will get the output? That original image is this one. Now out after the Sobel operator, it is just we are not going into the detail because we have a lesser time as well. But what exactly will get this particularly output from the Sobel operator. Now the Roberts edge enhanced edge detector. The Robert edge detector is based on the use of only 4 elements, that is the 3 by 3 mask. Roberts mask is basically will get the x plus y. There is no any another mathematical operation used in that case. So here we'll get the mask x and y values will get, and we get the again the Roberts filter. The output is here. So again, the linear feature is more enhanced over here. So Robert edge detectors is here because today we need to emphasize on the edge detection because the topic is given to me that edge detection and edge enhancement. So what is the purpose of that Robert Sobel? Here we can enhance the linear feature. We enhance the edge. We detect the edge, and that's why we are using this particularly Robert Sobel edge detectors over here. Now the Chris edge detectors, again it name suggests that it is an edge detector filter, and we know that edge detector filter suppresses the surrounding values like that. Now Chris non-linear edge enhancement calculate the gradient over here. So here is the formula. I'm not going to read line by line, but here is the value that will get the Chris window. Here is the formula is formulated over here, and we get the output like that. Again, it is uh, this filter will get this type of output from this original. So this is the what exactly the Chris after the using the Chris detector will get the output value over here. Again, it is an edge detector, so linear feature is enhanced over here. So this is all from my side. Let me show you one because due to the time, actually I already told Dr. That I have a little bit. We have an hands-on training program in our college, and I'm supposed to be. I should be there, so that's why let me just have a little bit time. So, but I'm here going to show one practical example over in the ERDAS, and then we will have the next part. Okay, sorry. So let me show you. Yeah, let me again share you the ERDAS imaging. So shall I show you the practical part now?
Yes, sir. Please proceed ahead.
Yes, sir. Yes. So
Please.
ERDAS imagine, I am going to use the ERDAS imagine 2015 version is here. So I have, let me just check out. Okay, I got an image. Check, check. Huh. Yes. Okay. Let me just add the raster over here. because it should be stacked image, otherwise it will take much time. So the screen is visible, sir, na?
Yes, sir.
Yeah.
What you are performing, we are following to you.
Yes, yes. So this is an layer stack. Yeah. It is already stacked image, because we know that the we get data from the different multiple layers, and we need to stack one into the one single layer. So this is an stack img file. This is a raster actually, though is the raster, so it will take time. Yeah, yeah, this one. Now we need not to do this the arrangement, because it is already in the FCC. So now what we have to do here, we are going into the raster, then we need to spatial, because our topic is a spatial enhancement. So go into the spatial. So click over there, and the convolution. So click on the convolutions. What it did, it performed the image enhancement operations such as averaging, high pass, edge enhancing, or low pass smoothing filter. So these things are done in that particular convolutions. So click on the convolutions. I will show you again where it is. So we are in the home button now. So here we can see the multiple menu bars in the LDAS Imagine. So we are going into the raster one, because we are performing the raster analysis. So that's why in that we need to go into the spatial. Then here we have the convolution. I'm going to perform this only one task, because the time constraint is there. So convolutions, click on the convolution. So it is taking time actually. Yeah, convolution is open over here. So it is already the input layer is already taken by this. Now sorry, so take a 3 by 3, any what you can say, that any high pass filter, low pass filter, whatever you can take. So I just take the edge enhancement. So we know that so many convolutions are there, we discussed in the our theory part. So here we can select the edge enhancement. So select this 3 by 3 convolution, or 3 by 3 kernel, that is the edge enhancement. Now give the output in the same part. Let me just the same folder, and I will add the one folder over here, that is a uh, okay, edge enhance, and it's a little bit do the name. So nothing to do anything again, and just say okay. So I'm adding the layer over here. I'm selecting the which type of filter we are going to use. So here I'm using the edge enhancement, edge enhance, then give the output part and say okay. Yes. You need to do this only few things, and then we will get the edge enhancement filter applied on the original image. So process list is here. Now modeler is running over here on the convolution tool. So process is showing over here 10, 22, 23 like that in the percentage. Okay, now it's computing the pyramids for our image, output image. So whatever process is going on, it is showing in the process list. Okay. Okay, it is done now. So modular running model, it is done. Click this. Okay, we click on the close. Now we are going to take another viewer. So new, it's stuck now. Yeah, new, new viewer we can add over here. Now go into the home button, right click over here, open raster over here in the second window. Recently we are using the same folder, so you can age, click on the age one and just click over here. Okay, now let's say the folder. So you will get the little bit the different image over here, which can emphasize the age one. So now if we use the another filter, it will get another very different type of output here. So this is an output we'll get from the age enhancement. So this is what I'm that I want to demonstrate over here. So 3, 2, 1. So in another band sequence, you can get again the age is more enhanced than this. So here likewise you can use any filter from the raster and you will get the your appropriate output from this. So this is all from my side. Thank you very much, sir. And thank you also to Dr. Tendulkar sir, who is the principal of uh, Nyamurthy Tatasai Pathalle, Sapre Commerce College, Dadasai Pitre College. Uh, Sardar Patil sir, Vice Principal of the college, and all the colleagues, all the um, uh, colleges which combinedly work into that particular things. All, and last not but the least, all the participants who are the patient to listen me over a period. So thank you very much, sir. So given an opportunity over the very huge platform that is an international workshop platform. So thank you, sir. Thank you very much.
Kolekar sir, on behalf of देवरुख शिक्षण प्रसारक मंडल्स Atle Sapre Pitre College Devruk and all the collaborating institutions, I have no words to extend the vote of thanks. It was really a resourceful session, and one more thing that I could add here, that is, along with theoretical component, you demonstrated practical, and that will be more useful to all the participants. Dear participants, I request you kindly ask queries if you have, otherwise we will proceed ahead for the conclusion of today's session.
One more thing, sir.
Yeah,
If a participant have a query in that regard, so they can communicate. Please share my email ID to them, so they
okay.
can, because of the time constraint, they can ask on the, they can drop me mail in the uh, uh, mail me. Then I will trying to answer of their questions, sir. Definitely. Please.
Thank you, sir.
Job easy
Dear,
writing
dear,
on the
dear,
group.
yeah, yeah, yeah. I know your busy schedule because already a program on practical demonstration of GIS is going on at your institutions.
Yes,
Dear participants, considering the limited time at the credit of Sandip Kolekar, sir, he is ready to help you through email. You are requested to ask your queries through email. I will send his email in the group. Okay.
yes, sir.
Now it's time to extend the formal vote of thanks for today's resource person and dear participants. I request my colleague Pratiksha Mohite madam kindly extend the vote of thanks.
Sorry, sir. Good evening to all. On the behalf of Department of Geography, Atle Sapre Pitre College, Devru, I would like to extend my gratitude to our special guest, Sandip Kolekar sir. Sorry, sir. Uh, uh, Thank you, sir, to take out time from your busy schedule to grace the event. And thank you for the guidance and thank you to all the participants for your presence. Thank you all.
Thank you madam. On behalf of
Thank you.
all the organizers, once again, thank you very much, Kolekar sir.
Thank
Thank
you.
you,
Thank you.
thank you,
Thank you,
thank
sir.
you,
Thank you very much.
thank you. Dear participants, tomorrow be in time. Tomorrow we will start the session sharp at 4 p.m. as per the schedule. Kindly go through the schedule provided to you. Thank you.